Good morning, everyone. Today is July 22nd, 2017, and I'm broadcasting here live from the University of British Columbia. We're here at the John Chappell Natural Science Philosophy Conference here in Vancouver, BC. So I thought I'd give a little report on the goings on here. So I'm just gonna, I have the list of speakers here. So I'm just going to mention what the topics were, and if you guys have any questions about the topic, please feel free to just break in and ask a question, and I'll do the best to answer. So the conference started out on this Wednesday at 9 a.m. We had a greeting by David DeHelster, our president, and he had an impassioned message from Peter Marquardt. He was reading that message from him. He was getting a little emotional about the purpose of the CNPS, and he was reminiscing about all the different people who have been involved with the organization and have passed away. But I think that the main point was that he was saying, like, the founders, they really didn't care about like how many people showed up to their conference. What they wanted to do is to just have those people be able to talk and debate, and to save that debate on videotape. So we are carrying on that tradition by continuing to have our conferences. There are about 20 people attending our conference, so it's not that big. Everyone fits in this conference room here, so this is the room that we're using. But it's pretty nice. It's got projectors and screens and whiteboards all around. And we've had our opportunities to have our heated debates freely in person. So that's the advantage of coming here to the conference. You can actually reach out and talk to people directly. So I wanted to show you, though, that if you don't know, everything that we're doing is available on Facebook. So let me go ahead and share that. If I can type. So you just go to facebook.com and then you need to look up the CNPS, John Chappell Natural Philosophy Society Facebook page. So let me share that. I'm getting some noise. If you're not presenting, you don't want to speak, please mute yourself. Okay, let's go back to presenting here. So this is the Facebook page for the John Chappell Natural Philosophy Society. So if you go to Facebook and just put that into the search bar, you should be able to get our Facebook page. Now, we've been streaming everything live. So if you go to this Facebook page, we will have a live feed of what's going on. But we also have a list of all the videos which have been happening. So if you missed out anything on the conference, you can just come back here and you can watch all the videos. So they're all listed here in order. And if my computer would catch up, it would actually start showing them. So you just have to hover over the video and then it will start playing. So that's how you guys can go and see all the videos that we have done, which is quite a few. If you scroll all the way down here, so this is a fun evening that we had where we just went to Duncan Shaw's house. And we just sat around and had some wine and chatted. So that was different. But so you can, if you weren't able to make it to the conference, you can see everything that happened pretty much by just going to our Facebook page. All right, so but before I go on, did anyone have any questions about the conference? Any questions about the conference that you wanted to ask? Just to make sure. Anybody? Anybody? Okay. All right, so the second talk was on improving the CNPS effectiveness by Bruce Nappy. So what was interesting there is that he analyzed all these email chains that have been going on. So if you're not familiar with this, at some point, I think like Glenn Baxter started this tradition where he would have this email list of like 100 names, and he would send out messages, and then everyone would just reply to that list of 100 emails. So that's kept on going on. And I think there are about maybe 60 people on this email list, and I'm still not exactly sure where it's coming from. But he analyzed like over a couple month period, what's going on. And some of the interesting facets were that there are thousands and thousands of posts, like 7,000 posts. But out of that 7,000 posts that he looked at, half of the posts were generated by only about 7 people. So out of that list, there are just 7 or 8 super active people making all the replies, which is kind of interesting. It seems like it's all the statistics gathered were kind of an exponential thing, where there's hardly anybody, but those last few people, yeah, they're the big contributors. And that he did some other interesting calculations, like the number of hours it takes for any one message to be processed by all these people. It's like in total it might be like 25 hours spent by the group processing just one email. So when you send those emails, be careful. You're like wasting almost a whole day's worth of effort by everybody to process those emails. I know myself, I spend probably maybe 15-20 minutes per day. That's usually my routine. I get on the bus and I will go through and read all these email messages, typically maybe 10 to 15, but sometimes people get out of control and it becomes like 30 messages and I just can't handle it. And I just select all those messages and delete them. Or what I do is anything that has the word relativity in it, I just send to my junk folder, since I don't really want to respond to issues like that. But it was interesting to see the analysis that he was performing on all our emails. Now, he would rather we stop using the email chain altogether and and use the new CNPS forum for all of that. So we would once again still encourage people to go over the forum and respond there, although even I myself don't use the forum because it's just too darn easy to just, well, and I really don't even have the time to process what's coming in my email, let alone go over to the forum. But that was a talk by Bruce Nappy about that. Then we had some talks by Cameron Reginald. So he was talking about, he has a very high interest in astrophysics. So one of them was about why the jet streams coming out of quasars are so highly contaminated. So it seems like his idea was that around the quasar, collimated. Yes, okay, collimated. Glad to see you're out there, Harry, awake. Well, like you guys said, if you have any questions about
that means that it's in optics, collimation means that it's aligned along the optical axis.
Aligned along the optical axis. Well, I think when it comes to jets, the streams of the quasars, that meant aligned along the rotational axis. Because it's like it rotates and then it sends out these two very tight beams north and south. So it seems that his idea was that the negative and positive charges separate in the quasar as it's spinning around. So that creates magnetic fields, which kind of bottle up the charges, which cause it to spit out either a negative or a positively charged beam. Was basically that what was his hypothesis there. Then his second speech was on the solar system as a result of random collisions. So he was saying something about Hubble's constant being involved in this, although I'm not entirely sure exactly what he was trying to say in that particular speech. So I don't think I can say very much about that. Okay, now let's see. What is the next speech was by Raymond Gallucci, saying, "Who needs dark matter? An alternative explanation for the galactic rotation anomaly." So I believe that his main point was that if you take into account magnetic effects, that you can account for the rotational anomaly that way. Apparently borrowing this idea from the electric universe people. But I believe that was the main point of that speech there. And then we had another speech by him. And, can the varying light speed explain photon-particle interaction? So here, we always hold the speed of light constant in our equation. So he was just exploring the idea of you explain the experimental results if you change speed of light and let everything else vary, like the frequency and stuff like that. So that was more or less, I believe, like a mathematical exercise, if you allow that to change. But I guess you've got to change one thing or another in order to match the empirically observed results. There, pal. And pal, if you're going to show your camera, we should at least see your face. We see you have a lovely jacket with stars and stripes. It must feel like singing the national anthem. Okay, so going on. So the next speech was by Cameron and about the sunspot cycle, gravity, and magnetism. So now this was something about how the coronosphere of the sun is like millions of degrees, for which there is not very good explanation for why that is, and how nothing should really be stable under those conditions. But I believe the main hypothesis here was that as electrons are emitted from the sun, they go out a certain distance and then they return back to the sun by, I don't know, gravitational or charge attraction. But because of the magnetic fields that exist, those electrons are constantly deflected and create a very chaotic situation near the sun, which I believe he says explains the extremely high temperature. It's basically this huge traffic jam of electrons that can't get out once they're emitted from the sun, is his hypothesis there. Let's see here now. The next speech was from Musa. The proposed experiment to disprove relativity. Actually, we haven't actually heard it yet. He's from Africa, and he got held up. I believe we'll be hearing his speech today. And so the next speech was on Raymond, the alleged lifetime. Keep on muting you there, pal. The alleged extended lifetime of atmospheric muons. So does this really confirm relativity? So I believe the main hypothesis here was that they just measure the number of muons that hit the Earth, and they calculate that all the muons are created exactly one level in the Earth, and that so they're missing a certain amount by the time they come to the planet. But the hypothesis is that the muons are not created in just one particular level in the atmosphere, that the muons may be created throughout the entire atmosphere. So if you think that the muons are created throughout the atmosphere, then you would think that the ones that are closer down would be able to reach the Earth because they have shorter distances to travel. Therefore, they don't need the longer lifetime because they're seeing more than they expect. So that is the main hypothesis, I believe, in that speech. Then we had a speech by Duncan Shaw. So Duncan lives here locally in Vancouver, BC, and he was the one who hosted us for the evening get-together at his house. But he was proposing a ether concept of gravity. So this is basically a push theory. He's trying to solve some of the basic objections for why a push gravity would not work, or how you explain things. So I think his main difference in his hypothesis is that he believes that it works sort of like the water cycle, where you have the water just gently evaporating from everywhere, and we really don't notice that at all, and it really doesn't exert any force on us. But when we feel it as rain coming down on us, then definitely we see the rain, and that rain can exert a force on us, and that's what keeps us coming down. But that kind of explains, like, if everything goes in, then something must go out. And how does it go out? It goes out basically by a process of evaporation, which we don't see. So he tries to explain that, and like any excess heat would escape with that evaporation as well. And the reason why this ether rains down on us from space is because when the ether reaches the coldness of space, it condenses and comes back down to us as basically in ether rain. So that is his basic hypothesis, I believe, on explaining why we have gravity. It's just a worse form of what we normally experience here in the Pacific Northwest, which is rain. So I'm kind of wondering, since he lives in the same area, whether that influences his thinking there. And so I gave my speech on how to win the Nobel Prize by finding the mysterious and much maligned ether. So this was actually 3 main points. So the first one was basically how the Nobel Prize committee is suckers for people who find particles. So no matter what particle you have, if you have an ether theory, all you basically need to do is find that particle and they will just hand you the Nobel Prize, no questions asked. Right? And I'm not sure why they're so impressed by finding a particle. I mean, after all, you're just finding something that was already in nature. You know, that's like finding a rock and going, oh, look what I found. Oh, I get a Nobel Prize for that. Great. Right? Not like you invented LED lighting or CCD camera or the integrated circuit or anything like that. All you did was find something that was in nature. But so that was the first point, is that, you know, Nobel Prize is a sucker for finding any new particle. So, and the second point was the second part is I propose that particle is a positron electron dipole. So the second part of the speech was all about, and I must have given like 7 or 8 different possible experiments that someone could do that would actually prove that thing exists. Because I feel that, you know, amongst the people in distant science, it's all talk. You know, unless you can do an experiment, which can only be explained by your theory, and experiments have to be pretty clever to do that, it's all talk, right? You can have, I think perhaps one of the things that was kind of remarkable was that we seem to be drawing some kind of consensus over that there must be an ether, and several people have come together to propose this or think that a positron electron ether is possible. Much to the dismay of David DeHilster, who has had a different thought on that. So he's feeling a little bit left out of the party. And so I had a bunch of experiments on how to find that particle. I need to convince someone to actually find that particle because basically I can't do it. I mean, I don't have the theoretical background for example, to do some of the perhaps complex calculations that would be necessary to predict what would happen to particles inside a pos-electron C. And then I don't have the equipment to actually do the experiment, whatever that experiment may be. So I have to convince somebody through the incentive of winning a Nobel Prize to do my experiment. Because the other possible reward for this would be opening up a new avenue of physics. And finally my last part of my speech was about, you know, what can the pos-electron C explain that we don't already know. So, you know, I explain things like it can explain the properties of space. You know, why does it have a speed of light? We can explain other things like magnetism and charge and how gravity works. And all of those things, which seem very different, can be explained as the result of a single medium, which is just that pos-electron C. So that was my speech on how to win the Nobel Prize by finding the ether particle. So I'm not sure whether I convinced anyone to go out there and do that, and I have my doubts whether anyone will actually take me up on my offer to go find the particle. But if not, I'll be here next year. So Now, the next series of speeches was from Lori Gardia, and she's like a computer programmer and an artist. And I think this is what happens when you are completely obsessed about a particular mathematical concept, which in this case would be the Mandelbrot set, which is this like pear-shaped um, fractal. So, she extended that whole concept to actually black holes and how the interior of the black hole is like the middle of the Mandelbrot, and like the Schwarzschild radius is the outer part, and then the photon sphere is the gray part on the outside of the Mandelbrot. And yeah, so that's like taking your passion for Mandelbrot sets just to the maximum. But she says that they're doing studies that should be able to reveal the shape of the outline of the black hole. And when those come in, she's hoping that they're going to say, "Hey, it's pear-shaped," and that's going to throw a gigantic monkey wrench into everybody's thinking, except for hers, because she thinks it's shaped like the Mandelbrot set. She also brought us some other interesting things in that there's some other things like atoms that apparently have come out to be pear-shaped. So she thinks that the Mandelbrot set has something to do with atomic shape because we see that pear shape on the nucleus apparently. So, while it seems like a crazy idea, well, maybe she's got something there. But if they come out and say there's a pear-shaped black hole, then it's like, okay, she's right. But that was her talk there. Then we had another speech which basically kind of complemented mine, which was a medium for the propagation of light revisited. So in this particular speech, she cites the work of Simony, who has the Epola theory, and went into detail about how the speed of light can actually be expressed as basically the same as the speed of sound formula in materials, and that if you treat them both the same, you can calculate the speed of light, and it comes out to the observed value. And so that is, I think, pretty strong evidence that that medium exists. Now, this is something that you can do with the positive electron, see that you can't do with any other ether, because most ethers like Duncan's, they actually really don't know what their ether is made out of. That's just postulated that there's some particle. But of course, if it's some particle, then we have absolutely no idea what its physical properties are, and that you can't perform an experiment on a particle where you don't know what its physical properties are. But if you have a positron electron, we do know exactly what those physical properties are. We can measure how much energy it takes to break them apart or put them together. That ends up being exactly what we observe as E equals mc squared. The energy that is expressed in there is actually the binding energy, much like the binding energy you would get when you're forming a water molecule. So when two hydrogens and oxygen get together, they release some energy, just like a positron electron getting together would release some energy. And in order to break apart a water molecule, you've got to put some energy in. And also to break apart a positron electron pair, you've got to put some energy in. And that is what's going on with E equals mc squared. It's not any conversion of matter to energy at all. That's just the binding energy. But she did a pretty good job of expressing the details of that medium. So I have another person in the conference here who believes that positron electron dipoles are a possibility for the ether. And then the next speech by Raymond was called The Ponderable Ether. So Raymond's an interesting guy in that he basically doesn't have his own theories. So I think David de Hilster said he used to go around saying that, but now David's got his particle theory. So and now he's completely as bad as the rest of us people who have theories, going around saying I've got the right theory and everyone else is wrong, and yeah, we all do that. So, and we all feel that no one pays any attention to us. So, welcome to the club. But Raymond, he doesn't claim to have any particular theory. So he evaluates these possibilities, I think, in more of an objective manner, since he doesn't have a dog in the fight. But he explored whether there is an ether and whether the Michelson-Morley experiment proved that the ether didn't exist. And so he discusses his issues, and I think he feels that a lot of things would be more easily explained if such an ether exists. So I think he kind of made the argument that the ether, likely does exist, and he presented his evidence as such. Let's see here. Now the next speech was by, let's see here, Eric Ryder. So he was.
So why do you conclude that the ether exists? You sort of left us hanging there. What was the basis of his conclusion that an ether exists? You left us hanging.
Well, like I said, he brought up like the Michelson-Morley experiment, wasn't basically null. That everyone says it's null, but it just came out to be much less than the orbital speed of the Earth. And that Dayton Miller did more detailed experiments. He did it in a mountain, and he came up with something that looked like some sort of ether wind, and how that these kind of things kind of ignore the possibility that the ether is entrained, and that's why we don't see the full speed. Things like that. So, but if you, like I said, all of the videos, the complete videos are available on Facebook, and you can watch the full 45 minutes. So all I can do is give you a brief summary, and but I'll happy to answer any particular questions like that one. So, like I said, anytime you have particular questions about the speaker's subject, just go ahead and break in. I'll see whether it jogs my memory anyway. So, because all these speeches are 45 minutes pretty much. And it's been quite busy, really. I haven't really had any time to go exploring Vancouver or anything. It's pretty much just show up in this room all day long, eat, and then sleep, and then come back and repeat. So it's been quite busy. I didn't want to miss anything, so it's been quite interesting listening to all this stuff. The other thing, the reason why I came to the conference is that I just flatly wouldn't have the time to even watch all these videos if I didn't come, because I would not have 8 hours worth of time to watch these videos if I didn't attend. So this is the only way I'm going to hear them. So it's another reason to go attend the live conference, right? Because you're just never going to have the time or the patience to watch all these things. Now, the next speech was an experiment in theory by Eric, removing all quantum photon wave particle duality entanglement nonsense. So, so Eric joins us on this on our chats here, and he has shown us his very sophisticated laboratory and all the experiments he's doing with basically the double slit experiment. So, but I think his main hypothesis is that photon as a particle is basically a bunch of hooey, and that basically everything on the light side of the spectrum is pretty much all waves. So he kind of shows that in his experiments. But I think one of the more interesting experiments that he does the opposite thing. He works with both gamma rays, but he also works with alpha particles, which come off of basically, radioactive smoke detectors. They spit out these alpha particles, and he bounces them off a thin gold foil. So some of those alpha particles go straight through to one detector on one side, but some of the alpha particles are bounced off and go to another detector. So that kind of splits the beam. So this particular isotope only puts out one alpha particle at a time, apparently, or so he tells me. And you can run experiments to show that. But the mysterious thing is that what he's seen is the experiment, which I still really can't explain, is that he'll see a particle register on both the left and right side of the detector at the same time, which means you had to have an incoming alpha particle. It would have had to basically duplicate itself, one part going to the right detector, the other part going to the left detector. So it's like he was seeing two particles when there was only one originally. So that is completely mysterious. That seems to completely violate all our energy and mass conservation laws. And that's, but it kind of like suggests that an atom can be split like through a beam splitter into two actually equivalent pieces. So either you know the experiment is being misinterpreted, or you know he's found some way to duplicate matter. But nonetheless, he has that experimental result, and you can like read his papers, go to his website, and judge for yourself whether that miracle occurred or not. So I personally have no explanation for it. You know, maybe the alpha comes in, it knocks another alpha off the gold particle, and that's the one we see on the left-hand side. Then we see the alpha going to the right-hand detector. But you think that would result in at very least reduced energy. But he's seeing like two full-size peaks on the detector, so that kind of rules that out. But he does a lot of experiments. He's got very sophisticated setup. So, and I admire that because, like I said, without experiments, it's all just talk. Although even with experiments, then you have to talk about the interpretation of what's going on there, and it's just not very clear what's going on there. I mean, you get a result, it's like you got 2 for 1. It's like, what the heck's going on there, right? Does that prove that matter is like a wave and can be split in two? I don't think it does, but you know, you have to deal with that result. Now, if you had some theory which specified how that happened, you know, then we could use that to prove that hypothesis, I guess. But I don't think he has a particular hypothesis on that. Other than matter can be split like a wave. So that was highly intriguing. In the next speech, okay, we had a speech by Bruce Nappy on his space lattice theory. So once again, this is very similar to like the ePolar theory or the electron-positron theory, except he doesn't specifically say that, you know, the lattice is made out of positrons and electrons. He did, however, show this very fascinating YouTube video about bubbles. You know, basically, there's an experiment where we had all the identically sized bubbles, and what they'll do is that they'll raft together into like this they'll self-form into this hexagonal crystal pattern, and you can see that different areas will form perfectly aligned areas, and then there'll be other areas which are pointing in a different direction, and between you'll see dislocations between those. So I think one of his main hypotheses was that things things that we detect, like electrons or whatnot, are actually the result of these dislocations. Because some of the interesting things shown in the video was that if you like push this like grain boundary, you'll see that the dislocations kind of like zip off in one direction. And you see these dislocations fly up and down the border like they're some kind of zipper, right? So that kind of looks like a particle. And then he takes that particular idea to the extreme and saying that, if these dislocations can, look like a particle, then maybe those are the particles. And that, things like electrons and protons are actually these collections of dislocations, which is, a break in the crystal matrix, or you could basically say they're nothing, they're holes that you can visually see in the matrix. So it's just like making something out of nothing, I think was the comment. But I believe that was the basis of his hypothesis, and I think that's not terribly likely, but that would be the basis of his space lattice theory. Okay, then see, now Raymond has been a very busy bee, and he had several papers in this conference. And in fact, see, this is the proceedings of the conference here, and it's got everybody's picture in it, and it's got everybody's papers in it. So if you wanted this thing, I'm sure you could ask David, because we have plenty extra over here. So, but I'm sure if you send them, like, I think you can order them for like maybe $9 directly from the publisher, or whatever, or shipping. But these are the proceedings, and it cost us $15 per page to have something placed into proceedings, and we got a free copy. And Raymond had like 4 or 5 papers in here, so he's speaking quite a bit. So let's see, what was his another role for corpuscles in the double slit experiment? So I think, he was, let's see, what he was trying to argue here, something about if you modeled anything going through slots, like I think he said, like ball bearings, or steel balls going through a slot, right? That you could model that there would be some preferential distribution of those ball bearings that would cause something that looks like interference, but really it's not interference. It's just that when the balls go through the 2 slots, there's a chance of them hitting each other, and due to the angles of the way things come, they would tend to redistribute the balls as shoulders around a central peak, and that is what we observe as something that looks like wave interference, but actually has absolutely nothing to do with wave interference. So I believe that was his hypothesis there. And I was able to tell him about, he didn't know about this, and this is one of the good things about coming to the conference, because people will tell you about other things you don't know, that they've done this experiment, the slit experiment, with very large molecules like buckyballs. And that's 60 carbon atoms. That's a pretty big object. I mean, almost you can see that with a microscope. And they've observed this so-called interference with buckyballs through a double slit experiment. But so he didn't know about that, which is interesting. But I was telling him that I bet you they could do this experiment with like basketballs down a hallway if you just scale it right. Probably if someone was throwing basketballs down a hallway through a slot and into the gym, you would probably find the distribution of the basketballs would be like this wave interference pattern where there's a central hump where most of the basketballs are going. But on the side, there would be a preferential distribution on the shoulders coming from the basketballs that are basically hitting the edge of the slot, coming together and just preferentially landing in those locations. So the maxima and minima there are not due to the basketballs interfering and canceling with each other. It's just that more basketballs are falling in particular spots. And then he described to me that it's like these, if you've ever seen them, they have a box with a set of pins in it, and then you drop a ball on the top, and it just takes a random path down through there, and that creates like the bell curve. But you can imagine that if the pegs were in particular locations, that would cause it to show this interference pattern. We have the central hump and two shoulders, and it would have nothing to do with interference. So I thought that was a very interesting conversation. I mean, that's we come up with these things while we're here, and you would never get that if you're not here. So next year, you guys all got to be here, right? Stuff like that happens. Okay, let's see here. Then we had a series of talks by David DeHilster, and he was basically comparing models like the standard model and ether models and all these other models. And he was saying, I mean, I would agree with certain things that in order to have your model, it should be fully physical. And if you have certain geometries in your model, for example, a lot of people like to use toroids in their models. And he showed a couple pictures from that. And his point was, if you're going to use toroids, then you got to justify, why did it do that, right? You just can't say that it's a toroid and yeah, that's you just have to take that as faith. No, that has to be basically, you have to have some physical justification, right? So, for example, we can generate a toroid with smoke rings with a vortex generator. So you would have to, I don't know, say that there must be some vortex generator out there, and that's what's generating the toroids. But generally speaking, people who use toroids in their theories do not at all justify the physical geometry they're trying to express. So that was his point. That, that's
mainstream doesn't justify why they use particles.
No, they don't. Although I think that one is a little bit easier to swallow because we see things like sand.
Oh, it's easier to swallow a particle that is basically a non-physical entity because it shrinks to a point which is nothing.
Right, a point particle is very hard to take.
Yeah, point particle. But I think
this whole argument about you have to justify, I don't really think that's really. Anyway, that's my comment on that. I think that's, I don't see that argument holds water. Sorry.
Yeah, maybe it doesn't, but I'm just telling you what David was reporting. Now,
I think you need to have a mathematical background in order to understand what a point particle can do with a field. Fields can interact with point-like artifacts.
How are they going to do that?
With our Green's function. Fields
How's that going to work? How's the Green's function do that?
Yeah, then you have to go to, for example, Wikipedia and look up Green's function and fields and all those things.
I know what a Green's function is.
You do?
I know what a Green's function is. I'm an electrical engineer.
So then if you also know what the field is, then you know that the field can interact with the point-like artifact and that the Green's function indicates the response of the field on that artifact. And if you have a large swarm of artifacts, you get a deep impression in the field.
Well,
And
it's all basically based on
so,
mathematical assumptions.
yeah, mathematics is not an assumption. It is a method, it's a technology that you can use.
Mathematics is nothing but assumptions.
If you think so, yeah, we cannot talk to each other.
Well, read a book on mathematics.
I am a physicist and I'm a mathematician, and I wrote a complete Wikiversity project on, for example, a mathematical model of physics. And there the whole thing is explained with mathematics. Without mathematics, you cannot explain it. You can talk about it and talk a lot of nonsense, but you cannot explain it. With mathematics,
how do you know that? What's your basis for that assumption?
I'm an academic.
That's an assumption. That's not
I'm one of the worst sort that you think about. You call what the kind of theory science that I support to a large extent, not completely, but to a large extent, you call mainstream, and you say that cannot be true. Well, it can be true if you take mathematics as a proper technology, a proper methodology to understand physics. If you don't do that, the discussion stops.
But in
I didn't understand anything that you just said.
In mathematics, even calculus is an approximation. It's an abstraction from the physical world, the physical experiments that we do. It's an abstraction, which gives us great tool and great anticipatory power. The results in mathematics and impose that back on physical reality, I think there's a problem there. And that's why I'm not. No. Okay, go ahead.
You may be right, but you have to start thinking first about what mathematics and reality may have for a relation. If reality, physical reality has structure, and this structure has a foundation, and this foundation is similar in structure to a mathematical structure, then you can comprehend the foundation of physical reality via this connection. And that's how you can approach physical reality. You can start at the bottom by seeing what is the relation between the two and build up the theory. So you start with a good foundation of physical reality, which is similar to a foundation of mathematical structures, and then you study the relation between the two.
Right. Yeah, I think it's a tool. I think it gives good results, but does infinity exist? So taking the limit to infinity, does a continuous something exist? Like, for example, a current. As an approximation, we assume a continuous charge distribution, but we know experimentally those things don't exist. So the mathematics that describes it is very, very useful, but once you abstract to
by experiments, you can never reach infinity. In mathematics, you can easily do that. So experiments already limit you to take that step. You have to go to some methodology that enables you to go to the limit of, for example, a series of fractals that end up in a limit that's no longer a fractal, no longer a rational number. Real numbers form a continuum. Rational numbers stay countable. You can never prove these things with experiments. You can prove it via mathematics. There they have tools to manage these kinds of discrepancies. They have solved the whole problem from going from a countable infinite to a continuum, because there's a big difference between a countable infinite set and a continuum.
I think in contrast, let's say take into account, say, string theory. Now there is a theory which is a gigantic pile of blackboard equations.
Yeah, so, I don't believe in string theory, but I do believe in rational numbers and continuums and number theory. I do believe in field theory. I believe in partial differential equations. They exist. They are mathematical tools. String theory is a sort how space can react. Well, Green's functions are sorts how fields can react on point-like artifacts. But I don't believe in strings. And I think most of the string theorists are quite quiet now because their theory doesn't fit to experiments.
I think this goes into the philosophy of what is the purpose of math and physics. Like say math is like a tool, so it's like a hammer.
It is.
You use that to drive nails that attach 2x4s, but you don't build houses out of hammers, right?
Yeah, but you are built from something. You don't clutch into each other. Your atoms are being kept apart by something. There must be something inside of this whole structure that holds things apart. And physicists call it the Pauli principle, but they don't understand the Pauli principle, but it exists. If it doesn't exist, you wouldn't exist. You would be a single point or a space without anything in it.
Yeah, I think, for example, you have to give a hard example. Like if I was trying to work with my model of the positron-electron dipole, you would first have to start with what we know about like positrons and electrons, which is their electric field, which falls off by an empirically measured value of 1/r². So there's some math there. And based on that, then try and figure out what would these two particles do in close approximation. So that's another thing that you can do with math. And then you could match it up against a physical experiment if you came up with some kind of unique prediction.
Franklin, these ideas work perfectly in a solid material. There you can have holes that behave as positrons and electrons that behave as electrons. And there you are, what you have is a kind of hole theory. And that works in solid material, in condensed matter.
Well, I didn't want to make another. Let's see here. I'm getting a lot of noise. Let's see what might have some issue there, Harry. No, that's not Harry. Okay. But Harry made the comment about it's you don't have to justify your geometry, and maybe you don't. Although I find anything, there was a comment in this week's mail. I guess some Roger writing. He said toroids are an anathema. To which I said, "Amen." It's like nothing physical could be having to do with a toroid because it's such a complicated type of object. Although that is, of course, an opinion of mine. But yeah, toroids are complete anathema. But it's just more likely to believe in particles or structures which we can observe in nature, like a grain of sand. So we know that is like a little round thing. It's random surface. It takes up a little bit of finite space. Sand grains do not intersect each other. When you put them in a cup, they fill all of the space of the cup. Those kind of objects, which are like round spherical objects. And I'm not saying they're point particles, because you were bringing up this whole thing about, can anyone believe a point particle exists? And I personally don't believe that there's no such thing as a point particle, because we don't see anything like that in our visible nature. There's no such thing. We see things that are like sand, or we see things that are like atoms. There's never anything that's like nothing, that's like a point particle. So I can believe things with their spherical shape. Spherical shapes are good, I think, but as opposed to say toroids, if your theory is based around toroids, unless you have a really good justification for that, I just don't. I just think that is bad science. But I think that was
based
David's
on
point.
nothing other than your opinion, which doesn't seem to be based on any factual knowledge that I can see.
It's based on the factual knowledge that we can see things like sand. I mean, that's total factual knowledge.
That's not an argument. That's just oh well, blah blah
No,
blah.
that is a total argument.
An argument is that it's not an argument. Just go on with your presentation, and please don't interject your opinions.
Science is all about opinions. So how could you not possibly do that? I mean,
I agree that opinions are in there, but you're supposed to be the moderator, but all we get out of your moderation is your opinions.
And you will certainly get some of that, since I have to say...
I'm telling you, your opinions are wrong. You're going to get that too.
And you are free to say that.
I absolutely am, and I'm saying it. Your opinions are mostly just bunk. Let's move on.
All right, we have Harry's opinion. All right. Against my opinion. Okay. That's good. That's what we're here.
They're not based on anything. You don't have any facts. You just make up stuff as you go along.
Oh no, I got all the facts, Harry. Every one of them.
I'm sure you did. Let's just move on.
All right, let's move on. So that was David DeHilster's speech on models in general. Now, like I said, David DeHilster now has a model of his own, and he calls that the particle theory. So this theory appears to be similar to the pushing gravity type theories, where he is postulating that there is this particle, he calls it G1, which is basically everywhere. And that is the basic particle that replaces things like charge, electrons, photons. He didn't go into it in very much detail, so it's a little bit hard to tell what his theory is based on that. But for example, things like the propagation of light, that would happen by an emission of these G1 particles, but they would emit them in a compressed and rarefied fashion. So as this train of particles goes out, it looks like it has a wavelength, because as it goes by, we have this area of concentrated G1 particles versus rarefied G1 particles. And so that's how he would express how basically light works. So that would be a full particle thing, as opposed to wave in a medium kind of picture. That would be more of the ether particle. So, one of the things he expressed was that he feels a little bit left out, because all the other people talking seem to be converging on this ether medium kind of thing, and he feels a little bit left out of the party. Although his G1 particle, I was trying to point out, pretty much fills all of space. And anytime you have a theory where you have some physical particle that fills all of space, that most people would call that an ether. So, but for him, them are fighting words. So never call his particle theory an ether theory. Although, like I said, a lot of people who have very similar theories, like Al McDowell, you would say, yeah, there's an ether, but it's particles. It doesn't it may not transmit the EM wave, but nonetheless, that to be a non-ether theory, you would have to say that there's nothing in the vacuum of space.
Well,
at least no
did
physical
anybody
particle.
actually attempt to define what they mean by the word ether? Because I know a lot of people in the NPA like to talk about ether, but has anybody actually defined what that word means? Has anybody tried to do that in their
I don't believe
presentation?
so. I mean, but for like people like me and Lori, we tell you
Well,
what we
no,
think.
no. I'm asking, did any, I know, I listened to Duncan Shaw's presentation, and I have to admit, one of the problems I had with listening to the presentations that was discouraging was I couldn't hear the speakers on Facebook, which was very discouraging because all I could hear was a few mumblings, and I listened and listened and listened, and it was very difficult to really follow what was being said. But so my question to you is, did Duncan Shaw and any of these people who talked about ether define what that concept means?
No,
Anybody
no one
tried to do that?
gave this is what I mean by ether definition.
Are we talking about you, or did anybody say that?
No one to my recollection went into that detail.
So it's just an ambiguous concept.
Oh yeah, it's very ambiguous.
So it could mean anything to anybody.
It does mean anything to anybody. That's kind of the point I'm trying to make here is that, yeah, it's like David's saying that I'm not an ether particle theory, but I'm saying that by most people's definitions, that is an ether particle theory, so which is complete anathema to him. So it's just kind of ironic.
Well, I don't think it's ironic. I think it's just an issue of it's not really clear what people are talking about, nor is it clear what Einstein was talking about when he said there was no ether, which, of course, is another issue of discussion. So you say, it's kind of like it's the word that nobody wants to use because it's been banished from physics, so to speak, because it doesn't really have a meaning in physics anymore, so you really can't use the word. So to use the word sort of, means that you're not doing physics if you say ether because the word's been banished. That's kind of what's ironic.
Well, yes, that's definitely an effect. I mean, usually the analogy I give for any time you've come up with something where you don't know what it is, you can substitute that term with little green fairy. So anytime I say the word ether, you might as well be saying little green fairy. So I would say I have a little green fairy theory. And then you kind of get an idea, why is it mainstream doesn't pay attention to my little green fairy theory? Why? Because you're talking about little green fairies. So
because they banished little green fairies from discussion.
Yes, and so that's why no one pays any attention to it. So that's why people like me, I'm telling you that what space is made out of is a positron electron dipole. Call it what you will, but physically that's what it is. So you know what I'm talking about. When I say, I may call it an ether, but if someone else has some other weird conception of what that means, maybe someone thinks ethers are fields. That people do that, and then they'll think, oh well, you don't have to have particles because the ether is a field. But to make things clear, I say exactly what my space is composed out of. So that should hopefully clear up.
So the answer is nobody really defined what they were talking about.
People like me would define what they're talking about by saying exactly what it is.
Well, you just told me, and I still don't know.
Really? That it's a positron electron C? That's pretty easy.
You told me that space is positron electron pairs, which doesn't really mean anything to me, really.
No, why does that not mean anything to you?
They occur in semiconductors.
What are you talking about?
And there the positrons are called holes.
Oh, okay. So I understand what you're talking about. But he's saying that space is electron-positron dipoles, which doesn't really make any sense to me what that statement means.
So I'm just, to me, that's so intuitively obvious to the most casual observer. I'm really having a difficulty.
If you state this, then you still have to state and or tell what the electrons and positrons are coming from. What's the origin of these constituents?
They have always been there, and they've always filled.
Why?
Why? I don't know.
That's an answer. You don't know.
Yes. But I think we have adequate evidence to suggest that things like, paper exist, and you can ask that exact same question, where did the paper exist? And the ultimate answer to that would be, I don't know. But yet, the paper still exists. So that's not a problem.
Yeah, most of what occurs in reality cannot be observed. That doesn't mean that it doesn't exist. You need everything what exists and cannot be observed to be able to observe what can be observed.
Yes, I would agree with that. I mean, we can't see the air between me and my camera here. I mean, we could say, well, I can't see that. But we can perform physical experiments to prove that there is, in fact, something in between us by capturing the gas and compressing it and showing that it has.
Now go to the smallest particles that exist. Now go to the fields that exist, and now go to everything that disturbs the field, that artifacts, point-like artifacts that disturb the field. You cannot observe these separate artifacts. You can only observe them when they come in huge numbers and huge quantities, as swarms. So you can observe a swarm of artifacts. An elementary particle is hopping around and causes a swarm of hop landing locations.
Well,
the swarm of hop landing locations is a swarm of artifacts. So the electron is represented by a swarm of artifacts, and that can make an impression in a field. Other things, a single landing cannot make an observable impression in a field.
Well, we did have that discussion here at the conference. I mean, there's some question as to whether, say, electrons exist. I would say because we can see the track of an electron and a track of an individual positron in our cloud chambers, that we do have good experimental evidence that those individual particles exist and can be detected as individuals.
That's true.
I mean, we also have very sophisticated scanning tunneling microscopes now where you can spell out like IBM in individual atoms and you can detect them where they're.
But as soon as you detect an electron, if you catch an electron at one of these locations where it has hopped, and you stop there, you stop the swarm. At that moment, the whole swarm is gone, and the electron is gone. In fact, its wave function collapses. That's what mainstream tells about the wave function, that the wave function collapses as soon as you achieve the detection of an electron. The whole thing is gone. In fact, it is not gone, but something that was generating the electron is now doing other things.
Really? Do you really believe that?
I can prove it mathematically. I do it in my Wikiversity project. If you can read mathematics,
that's probably one of the biggest. That's just one of the most unlikeliest things in all of quantum physics.
I agree. It is difficult to understand, and you need to know a lot of mathematics to be able to understand it.
Does anybody else have any opinion on that?
Sorry.
I'm expressing way too many of my opinions as a moderator. So. No, not even Harry? Okay. Well, where were we? So let's see here. I think we've gotten through. Let's get back to the list of speeches. Okay, so the last one I explained was David's speech on models, and then we had his father, Bob DeHilster. He was giving a speech, and his speech was entitled "The Candle, the Light Bulb, and the Radio." So I'm thinking his hypothesis here was to explain that each of these devices, the candle, the light bulb, and the radio, have a different mechanism for releasing light. So this wasn't entirely clear, but it's like the candle and the light bulb, they actually emit, say, in their particle theory, I think they actually throw off and consume their G1 particles. Well, actually, the candle does. The G1 did, because something in the candle gets consumed. They are throwing off the G1 particles. The light bulb does not get consumed, so it's generating light in a slightly different way that doesn't consume G1s. And then the radio works in yet another way to generate these G1 particles without it consuming anything, or the G1 particles that come from the battery or something like that. So I don't think I can represent that speech very well. Once again, all these speeches, you can go and see their full speech on Facebook. Now, we did have this speech by Peter Erickson about the square root of -1. So I admit I was pretty much totally lost during the entire presentation. It was like being back in school and listening to some algebra lecture, and it just went on.
That claims that it doesn't exist, or what?
Like I said, I had a hard time understanding. I mean, for example, he put like the absolute value of 3 over the absolute value of 4, which we would consider 3/4. And he said that actually had something to do with it's actually 3/7. I think he had something to the effect that you had 3 over like -4 or something like that as a fraction. But like I said, I was just I didn't know what to make of that. So it was just a lot of math. So don't ask me what that was about, because I'm not sure what it was. So, then let's see here. We had a speech from John Eichter. This is a new mechanism for matter increase within the Earth. So this is presuming you believe that the Earth has been expanding for the past couple million years. And so one of the interesting points that I hadn't seen before is the fact that they think that this Earth expansion has been happening at actually an exponential rate over the past like 1.5 million years. It's like for the history of the Earth going back 4.5 billion years, it really didn't grow very much for like the first 3 billion years, like hardly nothing. It was just like totally flat. But just like in any exponential curve, as soon as you get going, then it starts going like this. So it's like this total hockey stick thing, and that the rate of expansion has been growing just exponentially. So he was trying to come up with the hypothesis on why is this happening. And so he brought up a lot of things like there's been cold fusion research, and that he believes that the material is actually coming from the sun, that the sun is throwing out all these protons and electrons, and that the protons can come in from the poles, and they can actually be conducted through the Earth till they reach the center of the Earth, where they can undergo these reactions these low energy nuclear reactions to create matter. Now, to answer the question of why is it exponentially increasing, he points to the special case that we have water on the Earth, and that the water actually mediates the reaction, and as this happens, it actually makes more water, so that it's turning into some kind of feedback loop where we're getting more water, we're getting more matter made, and that's what's causing, that is providing the source of the additional matter that's being observed. So, and then we had our keynote speaker, Dr. James Maxlow. He flew in all the way from Australia to be at our meeting. So we are very thankful for Mr. Maxwell coming over. And he gave his presentation on expansion tectonics. And probably many of you may have already been familiar with the kind of thing. We had Neil Adams here at the forum at this talk once, explaining the basics of what the observed spreading is. And so he actually had one of these little globes which showed all of these stripes showing at where all the times match up. So each stripe represented a different time. Because that's a question I asked, which is, how does he know that this, growth is happening exponentially, right? So, and, he was saying that, we can measure the age of the ocean floor radiometrically, I guess, and we can kind of gauge that as a type of a clock. Although, what still seems unresolved to me is that, well, if the rate of expansion has been increasing exponentially, then shouldn't the youngest stripes be the widest, and the oldest stripes be the narrowest? Because, at the very beginning, the expansion is very slow and it's speeding up very quickly. But the stripes seem to kind of show the opposite, that the older stripes seem to be the thicker stripes. Seem to be expanding slower or something. Hello. See, we have one of our other people here at the conference here. This is my Saturday morning chat. Say hi to everyone.
I made it 38 minutes from how long does yesterday took me an hour. I did it in 38 minutes today.
All right. Yes. See, our main conference here begins at 9:00 a.m. So currently it's 8:30. So we still have a half an hour, but people may be filtering in as time goes on. So you can feel free to join our conversation if you'd like. We've just been talking about the various speeches that have been going on. So
say hello to those people.
Hello.
And I was explaining about, so we had James Maxlow here, and he had many slides to explain his points. And at the end of that, we gave him the Lifetime Achievement Award. And after that, we went to a nearby restaurant. They have a restaurant called The Point, which is very nice. It's like any standard sit-down restaurant. And we were able to order whatever we want, and we had a nice dinner with Dr. James Maxlow. And I would like to comment that here in the buildings here, this is a brand new building. This was completed in 2016. So the facilities are quite nice and modern. In fact, all the buildings around here look like they were built yesterday, pretty much. And it's really kind of hard to find an old building here at the University of British Columbia. So it's just the lap of luxury here at the University of British Columbia. So we thank them for providing such great facilities. And so that brings us to today and our upcoming. So I believe I covered all of the speeches which have been given so far. And that's what's been going on.
Will these videos be published anywhere?
Well, currently they are on Facebook, but as Harry mentioned, all we have to do the Facebook video is a cell phone, which is just sitting on a desk far away from the speakers. So if you speak quietly, then people can't hear. But if you're like me and jumping around and speaking loudly, then it's okay. So some of the videos you may have a hard time hearing the speakers because they're just not talking loud enough. But David is also recording each of these videos in high quality, and hopefully all of those will later be posted on YouTube. But the live feed is
I was missing on Facebook the title and the name of the presentator. I see videos there, but there's no indication what is treated there and who was the presentator.
Well,
I just see the video.
At least the name of the presentator listed there.
Yeah.
So let's just take a look at that. So make sure you didn't miss that. Let's see what we put up here. So here's the main website. So here we have some pictures of the award here. And there's something about Occam's razor. So we have published by David de Hilster. Let's see here. So I thought there was something that said who at least the author was.
I don't see.
Well, let's see. This one does. See, this one says David de Hilster at the top.
Yeah. I know the guy. So that's no problem. But some of the people I don't know.
Yeah, some of the Well, would it help if I went and added in comments, who the speaker was and what the topic was?
It will help.
Usually you can tell what the topic is by the opening slide usually. So maybe we can go by that. But yeah, it doesn't look like.
I didn't try that. I just opened it. And who are those people on the table?
Well, these are all the people who
participated. Defines what people are visible there.
Yeah, these are all the people who are here.
Yeah.
There's Duncan Shaw and there's Bob de Hilster. And we're all just, sitting around chatting until the late night.
It must be very nice and cozy there.
It's nice and cozy there, so you might recognize someone there in the middle of the table there.
I see.
Sure. See all the fun you guys are missing? See, this is Bruce Nappy over here, see? Yeah, I can type his name, right? Yeah. Type in it so people know. Bruce Nappy. Right? And that's Raymond over here, see? He gave like a zillion speeches here. They can help fill some blanks in there. And this is Duncan Shaw's lovely home. It's nestled in amongst all these like mansions. And there's our big poster that David made up for us. It's got everybody's pictures. This is like James Maxwell's favorite vacation picture, where he's declaring that, yeah, this all works. Australia didn't come from where the plate tectonics people said it came from. So while we're a small conference, I think it's been very intimate. We've had lots of opportunities to debate amongst ourselves and hear a lot of interesting topics.
Yeah, you had many nice presentations.
So hopefully when these all gets translated up to YouTube, they'll be a lot cleaner, better production values and such. So that's that. But if you weren't able to make it to the conference, or you know of other people, tell them to come to our Facebook page. It'll be just like they're almost there, almost. But next year you all have to be here. So
it's still far off for me. If you come to Amsterdam or closer, then I'll join.
All right, talk to David. He's thinking about where can we go. That's kind of like a vacation spot, but you know would attract a number of people here.
In order to get enough people, you have to join, I think, in America or Canada or something, at least close by.
Yeah, I'm making fun of Bob the Hilster here.
Europe is too far off.
So there's Bob the Hilster, and here's David. So
when I sent in a revised paper for him,
I had a little bit too much time while I was watching their videos.
I just deleted it. It's sort of at 60 pages, and then 30, 20, now it's just 10. So it's really just the highlights from my original.
I had to wonder, is your article in the proceedings?
No, because
there are more people here.
I wasn't going to do it, and then I decided, well, because I've been so busy, and then I'll just put this in.
That's Cameron back there. He's got all the.
I got when I talked to him on Thursday night. So
Did anyone have any questions for Cameron about his contaminated jet streams or anything like that?
Your paper through email to me the reason at 10:30 or 11 or so. I have to leave.
Now, amongst all the topics that were discussed here,
have I got your email and everything?
did anybody have any questions that they wanted to ask? The group is kind of filtering in here, so if you had a question, the person who spoke may actually be able to answer. Questions?
I think I must first read your book, then I can give comments on it. This collection of papers is a good point to enable the discussion, but that I think that must be in the future.
So what did you guys, I mean, we already discussed a little bit about the ether, and it seemed interesting that there seemed to be some kind of convergence towards this physical ether particle theory. So does that mean that we're reaching a consensus, or do people are still just very skeptical about that whole idea?
I have no problems with either, as soon as you explain it as an interaction between point-like particles and a field. As soon as you do that, then I can understand your ideas about either.
And I can do it in about 20 minutes.
For me, I can explain everything with particles and fields.
It's hard to know. This is important. So you know, there's so much that you want to get.
All right. Well, we've got quite a few people here. Actually, it's getting a little bit difficult to hear because of everyone going on. So that's what's going on. Is that people, they come in early in the morning and they get together and we talk. And actually, this may actually be one of the more valuable aspects of the CNPS conference when you're attending live, is that you get that kind of specific interaction. But it is getting a little bit noisy, so if nobody has any specific questions about the conference, then we'll probably just be ending it. We'll just be ending the conference here. So
I think that's a good decision. Then it's becoming more and more noisy now.
It's becoming more and more noisy, and I want to join in on the conversation too. All right.
I wish you a good day. And wish everybody goodbye and much fun with all these lectures and theories.
All right. Well, then I'm going to sign off from the 2017 CNPS conference, and I hope to see all you guys here, say next year, or anyone who's watching, because it's very interesting, even with the small number of people we have here. I actually think I like it better when there are small numbers, because then everyone can basically talk to each other. Everybody knows each other, and we all get an opportunity to interact. But maybe next year we'll have 100 people. So, but until then,
Optimist.
here from the conference, okay? But we'll be signing off for today.
Have a good